Hi everyone. So let's go ahead and take a look at section 3 of chapter 20, and this one's looking at the specifics on what's happening in the capillary bed. So we already know that the function of the main capillaries is going to be this exchange of gases, nutrients, waste, and substances like that. So what we're going to do is take a look at, of course, the little details that are going on behind it, because it can't be that easy, right? Of course not. It can't be that easy. So this is how things usually happen. Usually oxygen, hormones, nutrients tend to diffuse from a higher concentration to a lower concentration. So oxygen, hormones, nutrients move from higher concentration in the blood into interstitial fluid. Carbon dioxide and waste products diffuse from a higher concentration in tissue to the blood. That's exactly what it says right there, right? And then smaller solutes, depending on, of course, with their size smaller, they can diffuse through the little endothelial cells. They kind of go through the intercellular clefts. Larger solutes can pass through fenestrations. We talked about those, sinusoids and fenestrated capillaries. Some substances can use vesicular transport, like pinocytosis, the substances are taken in through pinocytosis, and then they transport the vesicle across the cell, and then it can be secreted on the other side by exocytosis. So this is another way that can happen. But really, in order to make this whole process more efficient, especially here in the capillaries, is we're going to use something called bulk flow. And bulk flow is just this, again, this mass movement of moving fluids out of the blood vessel or moving fluids into the blood vessel. It's just a more efficient way to move things in the capillaries. So that's what we're going to be taking a look at, is bulk flow and moving fluids and how they flow down a pressure gradient instead. So this allows large amounts of fluid and dissolved substances to move instead of waiting for smaller, or not small, I guess I shouldn't say smaller, but diffusion is going to take a little bit of time to happen. Diffusion is great for whenever we look at it in the respiratory system, when we look at it in the digestive system and things like that, but bulk flow is going to be the most efficient mechanism here in the capillaries for this whole process to occur. So the direction that these substances are going to move, and usually when I talk about it, I'm going to talk about fluid movement. So just think, whenever I do say fluid movement, there's going to be these dissolved substances that are going to move along with it. But the direction is going to depend on the net pressure of these opposing forces. So we're going to take a look at hydrostatic pressure, and we're going to take a look at colloid pressure. And this is going to really determine the direction of flow. So the bulk flow that's going to happen here in the capillary, the movement that's going to happen is either going to be filtration. Filtration is going to be exactly what it sounds like. Whenever you kind of filter your coffee, right? You kind of filter it through this coffee filter. You filter it through a coffee filter, and you push out what you want in your coffee, but you keep the stuff that you don't want in your coffee behind, hopefully. So like all of your coffee grinds. That's what's happening here in filtration. It's going to be how the fluids are going to move out of the blood through the openings in the capillary. So you get the good stuff that you want out of the blood and into the interstitial fluid, but you keep the things that you don't want inside of the blood vessels. And these are going to be things like plasma proteins. These are going to be things like red blood cells. Those larger solutes are going to be blocked and kept right in there. Filtration mainly occurs on the arterial end, and that's exactly what we want to happen on the arterial end. If you think about it, our arteries at this point, since we are talking about other systemic the systemic cells, and if we're not talking about the pulmonary circuit, they're going to be full of oxygen, right? full of nutrients. So that's what we want in the arterial end, is being able to move it out of the blood and get it out to the interstitial fluid, to where the cells are, so they can use the oxygen and the nutrients and things like that. There's another flow type called reabsorption. It goes in and basically sucks back some of the fluid that we just pushed out. But at the same time, it is going to get some of the waste, and carbon dioxide is going to also move in. And this is exactly what we want on the venous end, because from here, this is going to go to the heart, right? So it can go through the and get oxygen in the lungs and get rid of the waste and all that good stuff. So now we're going to take a look at the little details about how these movements are going to occur. How does filtration occur? How does reabsorption occur? Because it's not just that easy as, you know, putting your little coffee in there and clicking the button and letting the coffee maker do its job. No, it's never that easy in science. So let's introduce these pressures. Remember back here I talked about how it has to do with hydrostatic pressure and colloid pressure, specifically colloid osmotic pressure. So it's going to have to do with a fluid pressure, and it's going to have to do with this, this pressure that is exerted by the colloids in the bloodstream, and we'll talk about what that is. All right, let's first take a look at hydrostatic pressure. It is basically a physical force exerted by fluid on a structure. So if we think about, let's draw a very rough, oh, I just changed the, okay. So let's draw a very rough capillary bed like this. And just imagine that this side is blue. I didn't have time to change my pen. But what I really want to look at is, this is a rough capillary bed. It's supposed to look like this right here. Yeah, here's the arteries or arterioles going through the capillary bed. Just imagine that there's true capillaries coming off over here, and then there's the venules. But if this is the inside of the blood vessel, the physical force exerted by the blood inside of the blood vessel, well, that's just blood pressure. So this is what blood hydrostatic pressure is. It is basically blood pressure. It is, but here in the capillary end. So we'll talk about how this promotes filtration in the capillary. We'll discuss this in a second. We'll do some math. If you hate math, I'm sorry. It'll be really easy. It'll be just fine. But then there's always going to be two pressures here, because not only are we looking at the capillaries and what's happening in the vessels, but remember, we are trying to get the fluid out here, and this is the interstitial space. This is where I have all my little cells. These are cells, right? Let's say that this is, I don't know, the liver or something like that. And here's the cells of the liver. That's not what they look like, but, you know, just give me a little time. And then, of course, you have little capillaries that are going to, true capillaries that come off like this. But remember that that's what we're trying to do, is we are trying to get the fluid and get all of the needs to these poor little cells that are out here that need it the most. Back to what I was trying to describe. This in between the cells, remember, is interstitial fluid. Interstitial fluid is going to be the fluid that bathes the different cells. And if you think about it, it's going to be zero in most tissues, because the thing that causes blood pressure is really the pumping of the heart, right? There's no heart that's pumping out here in the cells, so that's why it's going to be zero out here and not on the inside. And on the inside it's going to be about 35 to 17, which we'll look at, or 16. So that's hydrostatic pressure. Again, you have one on the inside, and then you have one on the outside. Now let's take a look at colloid osmotic pressure. And this is going to kind of tell you where that the whole osmotic pressure is going to come from. So remember osmosis, and it's going to be that movement of water, and usually it has to do with solute concentration, right? Because water likes to move where there is going to be more solutes, right? Water follows solutes. So it's colloid osmotic pressure is basically the pull of water into the tissues because of the colloid. So what are the colloids in this case? It talks about protein. So these colloids, if you remember from your blood chapter, these are, if you remember the things that are found in the plasma that are going to help maintain osmotic pressure, those are going to be the albumins. Very good. So the albumins are going to determine this right here, this blood colloid osmotic pressure because of blood proteins. So we're going to talk about how these are going to draw fluid back into the bloodstream because water wants to be where there's more solutes, more proteins. This is going to promote reabsorption. And again, we'll talk about this in a second. It opposes hydrostatic pressure because if you take a look, blood hydrostatic pressure is going to kind of allow blood to move out. This is going in and drawing blood back into the capillary. And then of course remember that you always have the opposite pressure in the interstitial fluid. So interstitial fluid, colloid osmotic pressure is going to be the force drawing fluid into the interstitial fluid. It's not a whole lot. Look at that. There's not a whole lot of proteins. These guys, these albumins, they stay in the blood. They should stay in the blood. Only certain circumstances will they not, but they should stay in the blood. And they don't go out to the interstitial fluid. And there's not a whole lot of proteins out there in the interstitial fluid. So that's why it's 0 to 5 millimeters of mercury. All right. So let's take a look at some math right here. We'll look at this here in a second. But net filtration pressure is going to, it's going to be the difference between the hydrostatic pressure and the osmotic pressures here. You have to take a look at what's going on the capillary side, and you have to take a look at what's going on the venous side, not the capillary side. You have to take a look at what's going on the arterial side. And then you have to take a look and see what's going on the venual side because of the fact that there's going to be a pressure that changes over the capillary bed. And that pressure is going to be this right here. So because of that, this is going to actually change over the capillary bed. So this is the math that we're going to do. So let's go ahead and set it up and take a look at these different pressures here. So I'm going to kind of draw it out down here at the bottom. The next slide is will probably be a repeat of what I'm drawing, but I'm hoping to draw the numbers exactly where they are going to have the pressure. All right, so again, we are going to have this arterial side. I'm actually going to put my venual side. There's my arterial side. And let me go in and change my pen to blue so we can get that venual side working over here. Perfect. All right. So let's first set up all of these different, I'm going to use a black pen to write out all of these numbers. All right. Let's first go ahead and set up all of these pressures and see where they're at. All right, let's introduce hydrostatic pressure. So remember, this blood hydrostatic pressure is all it is blood pressure in the capillaries. So remember, it's highest at the arteries, right there at the heart, and as we leave the arteries, it's going to decrease. By the time it gets here to the very beginning of the capillary, it's going to be at about 35 millimeters of mercury. I'm not going to put the millimeters of mercury just to save time. So, but that's what that 35 is. It's going to be the pressure, that hydrostatic pressure. So, HPB. Let me write it, yeah. All right. So let's take a look. Remember, I just talked about how pressure is going to decrease as you move with distance. So by the time it gets down here to the venual side, your HPB I want to say half-price books every time I say HPB because that's what we call half-price books. But the blood pressure, the hydrostatic pressure here in the capillary over here on the venule side is going to be 16 by the time it gets here. Some books will say 18, some books will say 17. You know, you get it, right? Yeah. All right, this really is the only number that is going to change throughout this entire thing. All right, let's take a look at our blood pressure, or sorry, our hydrostatic pressure and the interstitial fluid. And that's going to be on the outside. It's going to be out here. It's going to be out here. It's going to be, you know, everywhere surrounding our arteries and our veins and our capillaries. Remember we talked about how there was no pump out there? So hydrostatic pressure is basically 0. Big bet 0. So there's our HPIF right there. It's going to be 0. So I don't have to do another one because it doesn't change. All right, so now let's take a look. So those are all of our hydrostatic pressures. Let me see if I can add another color in here. Oh, green, yes. I haven't used green. I'm so excited. Now let's take a look at our colloid osmotic pressure. So the BCOP, or COPB, that's going to be on the inside because that's the blood colloid osmotic pressure. Remember, this is going to be due to those plasma proteins. And it is going to exert a pressure of about 26. Again, I've seen other books that say 28. It doesn't matter. Just get the gist. Remember, this stays the same across the capillary bed because these little proteins, those albumins, should not be leaving. They should not be leaving, and they won't leave. So that's that. And let's go ahead and put a pressure for the outside. The colloid osmotic pressure of the interstitial fluid, it's going to be 5. Very few proteins out there. So that's what we have. These are going to be the different pressures that we are going to be taking a look at. So let's go in and calculate this. So here is, well, actually, I don't have to do it. It's right in front of me. So this is where they get these numbers. Here's the hydrostatic pressure of blood, 35, and there's 0. So this is going to be the difference between the hydrostatic pressures, and then this is going to be the difference between the osmotic pressures. So you see where they got it? They put 26 here. The other osmotic pressure is 5. Simple math. 35 minus 21 equals 14. It equals a positive 14. Anytime you see the net hydrostatic pressure as being positive, this is going to cause filtration to occur. So it is going to promote fluids and substances from moving out of the blood and into the interstitial space. So that's why it's going to be more prominent here on the arterial end. If we take a look, hydrostatic pressure, look at it. The net hydrostatic pressure is greater than the net osmotic pressure. So that's going to cause it to move from a higher hydrostatic pressure to a lower hydrostatic pressure. And it's going to promote filtration. That's exactly what we want on the arterial end, right? We want to move substances out of the blood and we want to move it into the interstitial fluid. So that is perfect. So let's take a look at the venous end and how it's going to be a little bit different, right? So again, what they did is they plugged in the same numbers. These all stay the same. The only thing that changed was the capillary hydrostatic pressure, or the HPB, right? The blood hydrostatic pressure, or whichever one. Again, the books will use different little nomenclatures for these. But if you take a look, they did the math again. So there's the difference between the hydrostatic pressures. And then there's the difference, again, between the two colloid osmotic pressures. But look, 16 minus 21 is a negative 5. Negative 5. It's really important. Where'd my negative go? It's really important to make sure that that negative is there, because anytime that you get a negative number, anytime that your colloid osmotic pressure is greater than your hydrostatic pressure, look what happens. that is going to encourage reabsorption because, again, colloid osmotic pressure, fluid is going to want to be where there's more colloids, and yes, they are inside of the blood at that point. You can't see them, but they are in there. Let me draw them for you. There they are. So that is going to be reabsorption, which is exactly what we want on the venous end right here. We want to be able to move fluid back into the venous end down here, because we need to get carbon dioxide in, we need to get the extra fluid that we just pushed out, we need to get wastes, all of that stuff. So that is going to promote reabsorption. So as you can see, there's a lot more filtration that occurs than reabsorption. So usually about 85% of the fluid that we pushed out is reabsorbed here. But you might be thinking, well, what happens to the other 15%? Because that's a lot. So let's say 25 liters per day is filtered out, and 85% is absorbed. I mean, that's roughly 21 liters. Sure, you're thinking, well, what happens to the other 4 liters? We can't have 4 liters that is going to stick around in the tissues. No, we can't. So that's why we have the lymphatic system. It actually goes in and it picks up all of this excess fluid that's not reabsorbed on the venous end, and eventually gets back into the venous circulation. So we'll look at this role in the lymphatic system a little bit more whenever we get to the next chapter, which is chapter 21. So let me kind of go back to this and talk about how, these numbers, they really do need to be consistent, because if there's any kind of issue whatsoever with a change of these numbers, it's going to go in, it's going to completely throw off filtration and reabsorption. So let's see what happens when, I'm going to stick with this green pen because I really like it, and I think it shows up pretty well on here. So let's say an individual has high blood pressure. Let's think about what number that is going to change and be an issue with. Well, it's going to be this right here, right? Because if we remember what this is basically the hydrostatic pressure that's inside of the capillary. And if you have high blood pressure, then that means that this number is going to be increased. Let's say it increases to 60. That means that this number is 60. And that means that this number is what? Check my math real quick. Is that 39? I mean, it's still positive. You're still going to get filtration occurring, right? Which is fine, exactly what we wanted. That's perfect. You're thinking, Ms. Watson, why are we even talking about this? There's filtration occurring. All right. Let's go over here, because since this number is high, this number is going to be high as well. Because yeah, even though it still decreases as it goes across the capillary bed, it's still going to be a high number. So let's just go in and give this, I don't know, 35. Because if you start high on one end, you're going to finish high on the other end. So that means this changes to 35. Not like me writing right there. All right, and look at this. 35 minus 21 is going to be a positive, not a negative. Remember, that's supposed to be negative 5. It is going to be a positive 14. Look, this is going to be, hydrostatic pressure is going to be greater than colloid osmotic pressure on the venous end, which is not good. That means that you have more filtration that's occurring on this end, and you're not going in and reabsorbing the fluid that just moved out on the arterial end. So you have all of this fluid that's going to be basically pushed out into the tissues, and it might get trapped there. Yeah, you have the lymphatic system to go in and pick up some excess fluid, but sometimes it can't keep up if it's that much. And so you have this fluid that's trapped in the interstitial spaces, and that's how edema can occur with hypertension. It's because of this whole imbalance between filtration and reabsorption. So anytime that you go in and any of these numbers changes, then it's going to cause big problems. Like with your colloids, let's see, if this number is different, let's say that you have a liver disorder and your liver's not making the albumin like it needs to. So, or there's an interesting thing called kwashiorkor that can occur in third world countries where there is a protein deficiency in children to where they're not able to produce proteins because of their diet. But it is going to drop this number. Let's say that it drops it to 10. And again, so we have 10 minus 5, if you can keep up with what I'm writing here. So that is 16 minus 5. That makes it a positive 11. So what you have is, again, you don't have reabsorption occurring on this end. And if you looked up individuals that have children that have kwashiorkor, they tend to have these really big abdominal pelvic cavities because all of this fluid that's being pushed out of the capillaries, instead of causing this kind of edema that you see with hypertension, it collects in the abdominal cavity. So that's why, any kind of change, dehydration changes it, injury to the blood vessel wall can change it, anything like that can change it. So anytime there's an imbalance, it can lead to issues like that. So that is capillary exchange, capillary dynamics, whichever one you want to call it. So now what we're going to do in the next section, we're going to be taking a look at how is the body able to go in and control how much blood actually goes into these capillaries. So the next section, section 4, is going to be taking a look at local blood flow and looking at how the blood that goes into the different tissues is going to be regulated. So until next time.